I am not going to stress. I have computer problems. I can't get the display up there, but we'll do something while we're waiting for people to come to help until that happens. And as part of my talk today, I was going to talk about loading and what loads we assume on buildings. And when we get to it, we can whiz through because we'll do that bit now. So when we load a building, when we design buildings, we design for dead and live load. We also design for, I'm just trying to get these spotlights off me. We also design for wind loading. If it's a pier underwater, you would have water loading as well. So all different types of loading. In this subject, we're limiting ourselves. Come and sit down. You may have to move in as Monday as well, not leave any gaps in the seating, please, because more people will be coming in. So if there are gaps in the middle, could everyone please move in towards the middle? And could people move in maybe towards the outside of the room? Because I've got people standing in the back. Anyway, we talk about loads, and we get those loads from standard codes of practice. So we don't make them up every time. We look them up in a book. When you come and do the problems, you'll get told the live load is this, the live load is that. So to give you an idea of what these loads actually mean, I have a square metre of sheet here, and I'm going to ask certain people to come into and come up here or down here and have a stand in this square metre of sheeting. So when you do get told the live load is 3 kPa or 5 kPa or 2 kPa, you can appreciate what that means. So when you're given the loading, it is normally in units of kPa, kilonewton per metre squared. I would love to write this down on a screen for you, but I can't as yet. Kilonewtons per metre squared. And what we assume generally, when we think of loads, you have to start getting a feel for loads. We normally assume a person weighs about 100 kilos, which is quite a hefty person. So 100 kilos, 1 kilonewton. So if we were designing a room such as this, you have fixed seating, we can't crowd in as far, but out the front, if you had one of the tutorial rooms you go in where seating isn't fixed, where you have your practice classes, a room like that would be designed for a live load of 3 kilonewtons per metre squared, 3 kPa. So I would like 4 people to come up and stand up here. Would you guys come up? Okay. Come on up. Come on down. Now, before we actually do 3 kPa, when we design a domestic house, we design it, and more, I need more. We design a domestic house for a live load of 1.5 kPa. Come on, up. Come on, please. Don't drop your phone. Okay, so for a domestic house, we of course don't put as much live load in there. So 1.5 kPa, 275 kilo people. Can I ask you how much you weigh? No, okay, I don't have to know. So let's put 2 of them in here to start off with. So if you were designing a domestic house, move in, okay, you would put this many people every square metre in the building, okay? And you would design for that level of loading. In some areas it may be heavier where you have bookcases, but otherwise in other areas it would be empty. So this would be a domestic house. In a room or the flooring out the front here, you would design this for 3 kPa. So can I have you and one other person, assuming you weigh about 75 kilos each, squash in there? One more person? I won't ask a girl now to come and join the crowd. To come stand here, and this would be, squash in, equivalent to 3 kPa. Yes, please. I can't. Well, first of all, this screen's not on. I've put it on laptop. No, it was working on Monday. Okay, and I put it on laptop, and it won't. And I do that, and I do VGA. And I did it on Monday, okay. But this is my mouse. I have a mouse, I'm very old-fashioned. So this is currently 3 kPa. Now, when we design a stadium, do you think the loading is higher or lower? Higher. A stadium, brilliant. Okay, and then I'll do with that. Having it like this? Yeah, okay. Now, when I do the freeze screen, I can do that. Okay, thank you very much. So what was the problem? Sorry. Oh. Okay, you've got us.
This happens more often than I wish it did.
Sorry?
This happens a lot.
No, stay here. No, I need you because I want to put more load on.
So what happens is you had it on an extended display, so it's treating The projector's an extended screen.
Oh,
So yeah, what you need to do is it's function and it's F4.
function F4. Okay.
Yeah, so when you press it, it'll switch to so this
Okay,
is
I've got to write that down, function F4, if I do that again. Okay. Because I've never had that happen before. Okay. Thank you.
no worries.
Okay.
Have a good day.
Okay, so this is currently 3 kPa. In a stadium, most of you said, of course, the loading would be higher. It would be 5 kPa. So we're currently at 3, so I need another 3 people to come on down. And that's why I said I won't ask a girl. So could 3 more people? Come on, anyone. Come on, come down. Please, gentlemen. So you've got to squash into that square metre. Squash right in. So when we design structures, we don't design with average loads on. Average loads means half the time things will fail. We have to design for extreme loading. So we all in there? So we need one more person. Thank you.
There we go.
Okay. So we would have that many people standing in every square metre of floor, and that would be the type of live load you would design a stadium for. Because, of course, in a stadium you can get people on people's shoulders, and if there's a riot or something, everyone crowds in on top. So you have to ensure that that stadium can cope with that level of loading. So, no, thank you very much, gentlemen. So now I can fold up my white sheet. Okay, now I can do this. Just give me 1 minute and we will get going. Okay, so I didn't panic too much with that happening, did I? Not bad, I did okay. Okay, so continuing on from... one at the diary here. Continuing on from Monday, I'll just go back a couple of slides and then we'll continue. We were looking at the structural forms and we said that they were a function of the structural actions. So in next week's tute, you'll be given a situation and you'll be asked what are the structural actions? Tension, force, compression, force bending, shear or torque. And each structural action has a corresponding deformation mode. So in compression, you all know it's shortening, in tension, stretching, in bending, curving, shear, distortion. So we have different structural forms, and those structural forms have corresponding structural actions acting. So in an arch, primarily, the structural action is compression. The members are in compression. Beams, it's bending and shear. Trusses, tension, compression. Cables, tension. So back in the old days where the primary building material was stonework or brickwork, I think we all know it's hard to put brickwork in tension. Okay, I mean, if you do try and apply tension force to brickwork, what happens? It cracks at the mortars. So thus, in the old days, when I went back to arches, most of the construction, I mean, they didn't think it through and go, oh, the structural action is compression, let's build out of stonework. Basically, because stonework is easy to build just by applying rock over rock over rock and stone over stone over stone, it is through compression loading. And arches, because arches work well in compression, you'll see a lot of arch structures from Roman times and Mesopotamian times still up, that are still standing. Then I said arches, we still do build with arches nowadays, but the structural material, we build them a lot slender looking, a lot thinner, out of steelwork, out of concrete, and here we have a truss, an arch that is a truss as well. You can see the triangulation. Second structural form I said was beams, being the most common, the easiest to build with. Then we had trusses, and trusses serve the same purpose as beams. They form a horizontal unit, you put a lateral load on there, and even though the truss overall looks like it's bending, when you look at each individual member, the members are primarily in tension and compression. Then our final form was cables, and I showed you with the pegs and the string what a catenary structure is, how when you move the load, the shape of the structure itself changes. And thus, we don't want structures moving underfoot all the time, so not many structures are made out of cables, even though they are probably the most efficient structural form. And I think I got to that point where I always have trouble pronouncing this, the Akashi-Kyoto Bridge in Japan. Has anyone seen it? Anyone been there? Okay, this bridge, completed in 1998, is the world's longest suspension bridge, a centre span of 1.9 metres. Our Westgate Bridge here, centre span 336 metres. So this thing is, what's that? At least six times as long, the centre span. When they originally designed this bridge, the centre span was 1,990 metres. And then there was an earthquake. And that earthquake actually moved both islands further apart, 1 metre further apart from each other. And because the construction hadn't finished, and it is a cable structure, and you know with cable structures, even when you hang bits of rope and string, they can move quite a bit without destroying the integrity of the structure. After the earthquake, they said, okay, we'll just change our design a bit and we'll continue building the suspension bridge. So the loads in these cables are humongous. The diameter, these cables have a diameter of 1.12 metre. They are massive. And within those cables, it's not one solid piece of steel. You have 18,000 wires, each of a diameter of 5 mil. And that is done so if one wire fails, you still have the other 18,414 wires that are acting. So there's a bit of redundancy built in there. Each wire can carry 39 kilonewtons, the equivalent of 4 small cars. The force in this thing is huge. You want to build one of those? You have to listen to what I'm going to say in the next hour. Okay, so many structures are made up of a combination of the different structural forms. Finally, you can see here, with the bridge here, there is a suspension cable, but the deck in here is made up, you can see all this triangulation of trusses as well. And that is to stabilise, to keep the decking more stable, more rigid. In Bunnings Superstore, we have beam members and triangulated truss members. And in this arch at Wembley Stadium, again, it's made up of cable, arches and trusses. So a lot of structures are made up of a combination of all those forms, meaning you have bending actions, tension actions, compression actions and shearing actions. So in summary, going back to Monday, what is a load path? It is a route along which the applied loads are transferred to the support. A few more of you would have had your practice class by now, so would have used this concept to work through why the Hyatt Regency failure occurred. So in terms of load path, you just have to ensure that this load path is not severed in any way. Of course, if it is, something will fall down. Secondly, the process of load transfer involves structural actions. So load is transferred either through the structure bending, squashing, stretching, twisting. And finally, the structural forms are defined by their structural actions. Okay, that brings us to the end of part 2. And now we're going to start looking at loads. And effectively, this topic I'm talking about now is the first question on the exam paper. So the way these lectures are given, each topic equates to a question on the exam paper, as well as a piece of information, a piece of knowledge you're required to have. So we're now going to look at loads, which is what I was doing with the sheet there. We're going to look at the types of load, the classes of loads and magnitudes. So first of all, now we're talking loads and forces, you need to be clear about your units. You need to understand units. Units of length, metres, force, we know kilonewtons, moments. A moment is a force times a distance, has units of kilonewton metres, newton millimetres. Doesn't matter what units you work in, as long as they are SI units. You can give a number in newton millimetres, newton metres, it's up to you, as long as you put the units after the number. Every number now should have a unit following it. In terms of loading, a uniformly distributed load is kilonewton per metre. So please do not get, I'm just trying to get my pen working here. Please do not get these two units muddled up as people do. A moment is a force times a distance. And then finally we have units of pressure or stress. Be careful with the term weight, it says. Okay, in scientific context, weight is the force on an object due to gravity, but in everyday context, it is often used to mean mass. Engineers, I don't know, I did engineering because I didn't get a very good mark for English. Sometimes we don't always word things properly. You may be asked to calculate the mass of something or the load of something or the force of something. In brackets after, you will be given the units we want it in. Okay? So be clear always what it is you're being asked to do. It may say calculate the weight in kilonewtons per metre. Now, we all know weight hasn't got units of kilonewtons per metre, so just pay more attention to the units than the wording is the point I'm trying to make here. So always look at the units, whether you're asked for it in kilograms or in newtons. So, gravity now, newtons. How many of you, most of you, I assume, have done physics? Okay? If you have, you'll probably understand this without any problem. If you haven't, you just need to listen a little bit harder. There's no very complicated physics involved here at all. So, force, to get a weight, it's mass times gravity. For ease of calculation, we're now going to assume gravity is 10. That just means we're increasing all our loading by 2%. It's a minor thing. It's just rounding up we do. So when you do your calculations for the next 11 weeks, gravity is always 10. So 1 kilogram force would equal 10 newtons. Sorry, a 1 kilogram weight would be equivalent to a 10 newton force. Okay? Now, on the moon, of course, gravity is 1/6 of what it is on Earth. So if you were working out what the force was on the moon, 1 kilogram would be 10 on 6 newtons. So we're on Earth here, we'll assume gravity is 10 in what we're designing. I also want you to get a feel of forces, which is why I did the sheet thing. I want you to start thinking, okay, I've got a beam here and I'm asked to put this much load on, what does that load mean? And to help you in that end, I suggest when you think of an apple, it's a pretty heavy apple, not really, 100 grams. Think of an apple as being 0.1 kilograms or 1 newton. So if you were given a beam now and you were asked to design it for 2 newton, you should immediately scratch your head and go, hang on, that's like 2 apples sitting on this beam. That can't be right. Maybe there's a problem with units. So you need to be able to flag when you think there are potential problems there and ask questions. So 1 newton is about an apple, the weight of an apple. A 1 kilogram bag of sugar has a force 10 newtons. One person, as I said, we assume they weigh about 100 kilos, so as a force 1 kilonewton. So if I say we're going to design this chair now for a load of it of 1 kilonewton, you can go, okay, that's about a 100 kilo person. That's about reasonable. And 1 car finally is about a tonne, so think of a car as 10 kilonewton. And try and remember those so you can get an idea of what sort of level of forces we're talking about. Now, as I said on Monday, structural design is what most of this subject focuses on, so I'm going to teach you about structural design. And that's where we come up with mathematical models of real-life situations. So as part of that mathematical models, we need to come up with idealised representations of loads, of how the loads act. And we assume 3 types of forces: point loads, uniformly distributed loads, and applied moments. So a point load would be a single bus on a bridge or a person here standing on a beam. So as the mathematical model here, we would draw it as our stick being our beam. I'll talk about the support types in a minute. For now, we've got a ball on one side and a triangle on the other side, and the weight of that person would be applied as a point load of weight P. We won't embarrass them and ask them how much they weigh. The second type of force we call a uniformly distributed load. And that's the most common type of force, or uniformly when we're talking about one-dimensional or two-dimensional structures. And that would be a line of people on a beam, or cars continuously piled up on one beam in a roadway. So the load here is now kilonewton per metre. So basically we work out the weight of everyone. So we work out the sum of all the masses here, and then to work out W, we would get the sum of all the masses, and we would divide by the length of the beam. And that would give us the load in kilonewton per metre. The final load type, which doesn't occur, and we refer to that as a uniformly distributed load or a UDL, which used to be what people drank in my day. UDLs. Do they still exist? Yeah? Okay. So now whenever you think of you're drinking a UDL, you can think of, ooh, uniformly distributed load. Okay. The final load type is an applied moment. Now, it's not very often a moment itself is applied to the beam. Typically, that moment is applied through an offset force. So here we have our weight here, and it's offset from the actual column D. So when it comes to designing the column itself, it would be designed for the weight here as a vertical force, and there would be an applied moment applied to it of value WD, which is the force times the distance acting. Okay? So they are the three idealisations, the three ways we apply load to our hypothetical beam, to our mathematical model. Now we'll move on to the classes of load. So what is this load we're talking about? Well, structures are loaded in different ways. Of course, with dead loading, that is the weight of the structure itself. Before a beam can carry any other load, it needs to be able to support its own self-weight. So dead loading, as well as being the self-weight of a beam, also comprises all the fixed attachments. So in this room now, part of the dead load would be the weight of the chairs, because they can't be moved in and out. So they're considered to be permanent. Also, the weight of the carpet, that's permanent loading, and the weight of the ceilings. So that would be part of the permanent loading on a structure. Then we have the movable component, the live loading. And that, of course, is people. If we're dealing with chairs and tables in a room that can be moved around, it would be furniture. On a bridge, it would be the cars. Then we have wind loading, earthquake loading, earth pressure loading. When you're down underground and you've got the basement walls, you have pressure loading from the soil acting on there. And then we have liquid pressure when we're dealing with bridge piers, and also basement walls if you're under the water table level. So you have all these complicated loadings to consider, but in this unit we're going to focus primarily on dead and live. Well, not primarily, we will only deal with dead and live loading, because they make up the majority of the loading on your general structures. So you don't need to consider the rest. Just be aware that if you were designing a building like this, you would also need to consider wind load. And if we were in an earthquake zone, you would then also have to look at earthquake loading, but not earth pressure loads or liquid pressures. So as I said, the dead load comprises the self-weight of the structure and all fixed attachments. In order to calculate dead load, we need to know densities of materials. And again, here are two standard densities that you will become familiar with in the next couple of weeks. And they're values that can be assumed. So again, concrete density 2,400 kilograms per metre cubed. So if I got my sheet again, that's 1 by 1, but think of it as a cube now of that shape, 1 by 1 by 1. That cube would weigh 24 kilonewtons. Okay? We said a car weighed how many kilonewtons? 1 tonne? 10. So if you crush up, you can have I always used to think, how many cars can you crush up into 1 cubic metre when you see them on the back of the trucks being transported? Well, about 2.5 cars. There are air gaps in between, but basically 2 cars would crumple into 1. Oh no, that's of concrete. In steel, what am I talking? 7 cars. If you look at the density of steel here, okay, steel density 78.5 kilonewton per metre cubed. If we say 1 car is equivalent to 10 kilonewtons, that means in 1 metre cubed, crinkled up, you could fit in about 7 cars. So steel is heavy. Concrete is heavy. It has 1/3 the weight of steel. So when you're given density of steel and concrete, quite often you will be given it will be given to you in units of kilonewton per metre cubed. They are not the units of density, but again, we're working in forces. So if you get it given to you in kilograms per metre cubed, you're just going to have to convert it to kilonewtons per metre cubed. So don't get stressed by your units. Now, all these dead loads, oh my God, do we have to work out the densities of everything and then work out the volume of everything? Yes, in this subject, yes. In general, no. There are standard Australian, New Zealand standard codes of practice that as a design engineer you would look up to work out the weights of things. And here is an excerpt, Table 2A2, from the Australian standard for material densities and weights. And then there you'll see standard material products such as galvanised standard corrugated sheeting. It comes in different thicknesses, so you won't have to get density and work out the volume of it. It then tells you here how much in kilonewtons per metre squared, how much a bit of sheeting, 1 square metre of sheeting would weigh. So you can look all these values up. In terms of live loads, again, there's a different standard, AS 1170.1. Oh no, it's the same one. That was the dead load component, and this is the live load component in there. So here we have ourselves in an institutional room where we are now, hospitals, schools, colleges, prisons, classrooms, lecture rooms. So there we are in the lecture room. I said the live load was about 3, and there it is there, 3 kPa. Don't worry about the concentrated loads. We also have to design for concentrated loads when we look at locally at certain connections. When we look overall at weight, we would put a blanket, what we call a blanket loading everywhere. When we come to design particular details, you would then say, well, let's assume we have a single concentrated point load. So we have 3 up here. Assembly areas without fixed seating, such as dance areas, vestibules, public lounges, is the 5. Balcony, if you're up with the news, you hear quite often there are quite a few balcony collapses. So balconies should be designed same as area leading into it, not less. So a lot of balconies have been built and not been designed to proper loading. We have bedrooms, we have boiler rooms. Why are boiler rooms heavier? More loading because they have boilers in there with lots of water in them. So the loading goes up, 7.5 here. Corridors, so we're talking of the order of 3 to 5 to 7.5 for live loading for buildings. So you would look them up. And when you come to do your project in a couple of weeks' time, when you start on it, the first thing you have to do is download an excerpt from the code and actually work out what the live loading is on your structure. So we're not going to tell you what it is, you'll have to look it up. We will guide you where to go. So typical live loads, as I said, houses 1.5, offices 3, lecture rooms with fixed seating 3, grandstands 5. So think 5 kPa, 3 kPa here, equivalent of 3 100 kilo people standing in every square metre. So if you were asked to design something for 30 kPa, you would go, wow, that's a lot of loading. Are you sure you've got, that's correct? Wind loads, as I said, there's a different standard, 1170.2. Wind loads are far more complicated because they induce loads on structures in different directions depending on the way the wind is blowing. And you get pressures and suctions and you get internal pressures, and you then have to look in great depth. You have to define where you are on the earth, okay? What latitude, what longitude, because the winds are different. Then you have to define whether you're in a hilly zone, in a flat zone, whether you have surrounding buildings around you. On a windy day, go stand in front of the Menzies building. Where are we? Yes, the Menzies building is over there. The wind forces there are huge, and that's because they're blowing around that big tall building, which is not surrounded by very much. So wind loading is extremely complex, and we will not cover it here. So units of force, I think we've been through this. Concentrated force is kilonewtons, line loads, uniformly distributed loads here. Kilonewtons per metre. When we're looking at forces on an area, if that's 1 metre and that's 1 metre, the loading here is on the plan area, kilonewton per metre squared, and the applied moment kilonewton metre. You need to be very, very clear about your units. And when you're doing your calculations, always put units in there. If you then get confused, you can then look at your units to actually work out what your answer should be. And if your answer is in the wrong units, you know you've made a mistake. So you have to start getting into the habit of self-checking yourself. Don't always say, where did I go wrong? See if you can work out your error yourself. Now for 2D beams, we generally work in units of kilonewtons and kilonewtons per metre. So this is what we're going to stick to generally. So let's look at some weights. So if you were dealing with the weight of a section, so the weight of a beam, and you want to know how much it weighs in kilonewtons per metre. Here we have a beam here, it's a round beam. Just a bit of terminology I want to get you used to, and I should have brought my beam in again, but I didn't. If this is my beam here, it's a bit small, sorry people at the back. The end view, that's what we call the cross-sectional area of the beam. So if we wanted to work out how much a section weighed in kilonewton per metre, our starting point would be, well, let's work out how much the whole beam weighs in kilonewtons. And that's volume times density. And that density there, if we're working in kilonewtons, that density there would be, if it was concrete, sorry, it would be 24 kilonewtons per metre cubed. That's for concrete, and 78.5 kilonewtons per metre cubed for steel. So you would work out the volume of the beam. Volume, if you look at that beam, your cross-sectional area there would be pi r squared times length. That would give you the total force. But we want the load in kilonewtons per metre. We want to know how much the beam weighs along its length. So if I draw a stick drawing over here of that beam, we basically want to know what this load W is in kilonewton per metre. So we would get our total load and then divide by the length. Now, our volume here is our cross-sectional area, A times length times density, and we divide by length. So at the end of the day, if you can visualise what's going on, to work out how much this beam weighs, you only need to get the cross-sectional area and multiply by the density. And that will give you the weight of the beam very quickly. Now, if you can't visualise that and go from that step straight to that step, I have absolutely no problem. If you in your mind, to get the hang of it, need to go, let's work out how much the whole beam weighs and then divide by the length, you do it however you get the right answer. You do it, you work out a procedure that you understand. There's no right or wrong here. There's a right or wrong answer. The procedure to get there is fine. So here we have a beam. The diameter is 50 mil, is 5 metres long. How much does it weigh? We have the density of steel given to us. So very quickly we can work out the area, and then the weight is just density times area. So what I could have done is I could have actually worked out the density, and I could have multiplied it by the volume times 5 metres long. So that number there is now metres cubed, and then I could divide by 5 metres. And if I do that, I would get the same answer. Now, one thing I haven't pointed out yet, which I can see I need to point out there, is you need to be consistent with your units. So the question asks you to work out the load in kilonewton per metre. When you're given this cross-sectional area here, it's given to you in millimetres. So in working out the area here, this unit here, the radius here is in units of metres. Okay? So you can't mix your millimetres and your metres and your kilonewtons and your newtons. You have to be consistent with what you're using. You can check yourself, as I said, always with your units. If you go, I have no idea what I'm doing. Well, let's look at the units of area here. So the units of area, we know are metre squared. And the units of density, in this case kilonewtons per metre cubed. And you can see here that we cancel out our metres and our units are consistent. So what you'll be given the week after next is you'll be given beams of different sizes, and you'll be asked to work out the dead and the live loads and how much they weigh and what the loading would be for you to design the beam. Here we have an example where we have a precast beam bought off the shelf. This is what we call a T-beam, or they call it a CUBE6 flooring system beam. And you're given all the dimensions of it. Its span varies. You see, so if you tell me how much the entire beam weighs, if you say, oh, Lizzie, those beams weigh 24 kilonewton, then I'll say to you, well, how long is it? So when we calculate the weights of things, we prefer to calculate the weights in terms of kilonewtons per metre. And then you can say, okay, well, my beam's 2 metres long, so this is how much it weighs. My beam's 10 metres long. This is how much it weighs. So when you work your loading out, always work it out in terms of kilonewtons per metre. Okay, so what will you do here? You'd just work out the cross-sectional area. This end area is my cross-sectional area. So it's 42 up the top. I don't know if you can read that clearly. It's 100 mil deep in here. So it's been worked out basically as 2 rectangle areas. We work out the area, in this case still in millimetres squared. We know the density of concrete, so density times area, you see the unit change shown in there. And we can see our beam weighs 0.21 kilonewton per metre or 21 kilos per metre. So if someone said, can you come and help me move these beams and they're 10 metres long, do your calculations quickly and go, no. Okay, because you're being expected to carry over 100 kilos. Okay, that's beams, slabs in car parks and floors in buildings. How much does a slab weigh now? Because we're dealing in 3D, does it weigh in terms of kilonewton per metre square? How much does every square metre of slab weigh? Well, once again, if you want to work out what the total load is, it's volume times density. So what's the volume? That's the thickness by the length by the breadth. You want to know what it is in kilonewtons per metre squared. When you work out this volume times density here, that has units of kilonewton. So we then need to divide by the plan area. That's the bird's eye view area. So in doing that, our volume here is B times L times T. Our plan area is our breadth times our length, is that area in there. And you can see again here, this time we cancel out B and L and B and L. So all we're left with is thickness times density. So if you're standing somewhere and someone goes, oh, I wonder how much this thing weighs, just go, well, if it's 100 mil thick and it's 24 kilonewtons per metre cubed, it's concrete, the thing weighs 2.4 kilonewton per metre squared. So you can very easily work out how much a floor weighs. We don't care what the whole floor weighs. How much does it weigh per square metre? And then you can work out what the whole floor weighs. Okay, we have a 150 thick concrete slab here. It's 4 by 5. How much does it weigh in kilonewton and in kilonewton per metre squared? So we can work out the volume here, the density, multiply volume times density to give you the total weight. And then if we want to know how much it weighs per metre squared, you can just multiply density by thickness, or you can follow on from this calculation here and just say, well, it's 72 kilonewtons, divide by 4 by 5, and that would give you 3.6 kilonewton per metre squared. Live loads are given to you also in KPA. In this subject, though, we're working in 2D primarily. So this footbridge here, if I was to create a mathematical of that footbridge, I would show it as one line, a single beam, with, again, we'll just call it a triangle and a roller support at either end, and I would need the loading in kilonewton per metre. So the question now is, how do I get from kilonewtons per metre squared to kilonewton per metre? Yeah? So we'll do the numbers, so I'll show you all how to do it. People get very confused by this. We want to know what the total live load is. We multiply the load by the plan area, in this case B times L. That gives me the total load. I want to know how much the beam weighs in kilonewton per metre length. So yes, I divide by the length. So if we turn this plan area into B times L, you can see our lengths cancel out. So a quick way to get from kilonewton per metre squared to kilonewton per metre, you just multiply by the width of the beam. Now again, people find this very confusing. If it confuses you, work out the total load. Follow your logic through. It's this much per square metre, my floor is this big, that'll give me the total load, and I want it per metre length, so I divide by the length. It's the same process. This way is just a bit quicker, but it doesn't matter. We have a slab here, 150 mil thick slab. It's 1.5 metres wide here, and it's 10 metres long. Carries a live load of 5 kilonewton per metre squared. So the question is, if I represent this as a stick drawing, like so, what is the weight on this beam? That's meant to be an arrow. Okay? What's the live load on the slab in kilonewtons per metre? So all you need to do is you get your live load 1.5 and your live load of 5, and you multiply it by the width here to get 7.5. Your units, if you look at your units, this has units of metres, this has units of kilonewton per metre squared, so that will give you units of kilonewton per metre. Now, if you're there sitting there going, do I divide by the length, do I multiply by the length, do I multiply by the breadth? Oh, I don't know what the breadth is, I don't know what the length is. No big deal, okay? Get your load 5. Say I'm going to multiply it by the full area, 1.5 times 10 metres. And I know that number now is in kilonewtons. And I want it kilonewtons per metre length, the length over which it acts. So I would now divide by 10. And of course, you end up getting the same answer. Do you need a break yet? Do you want me to tell you about something interesting for the first break, or do you want to have a time-off break? Interesting? Okay, the loudest person wins. I'll never resist an opportunity to tell you about something interesting. Oh, hang on, actually, you want a time break? Actually, my interesting thing doesn't come back. Where's my interesting thing? Okay, I'll give you a time break here and I'll tell you about something interesting when we do the... Okay, we'll get going. In these breaks, I can't remember if I told you on Monday, if anything is not clear, that's a great time to come down and quiz me. And then I'll go, oh, yes, I did explain that incorrect. I did give you the wrong number or do something wrong. Or, okay, I'll explain that when we get back from the break a bit clearer. So it's to your advantage if you come down if something isn't clear and get confirmation or get clarification of it. Now, these loads, I said they come from the Australian standards, but where do the Australian standards get them from? Why do you need to know that? You need to know that because you're going to be an engineer, a professional. And it's not enough just to know where to get it from. You've got to understand where it's come from where the book has got that information from. So where do all these loads come from? Well, unfortunately, it's not just as simple as saying it weighs this much or we'll put that level of live load on. All loads involve uncertainty. So in terms of live loads in a building, okay, you could look at get some observed load densities in office buildings. So we now are going to define our loads as being characteristic loads. We're going to have characteristic dead loads and characteristic live loads because all calculations involve uncertainty, so we are going to use some probability analysis to control this risk, this uncertainty. So we define all our loads as having a 5% chance of being exceeded, and we call them characteristic loads. So unfortunately, I'm now going to talk about Bell distribution. You've all done statistics in a very minor way, okay? So we're not going to do a lot of it. Characteristic dead loads. So you may say to me, but Lizzie, we can work out the weight of something. Where is the uncertainty in it? Well, dead loads may vary due to under or overestimated densities of concrete, because concrete does weigh different amounts depending on how much gravel and the constituents you put in there. And dead loads may vary due to materials used on site not being consistent. Or dead loads may vary due to the builder not wearing his glasses that day and reading 100 mil thick as 120 mil thick. So there is always uncertainty in your system. And based on the principles of probability, the accepted practice is to choose a value for the density that only has a 5% chance of being exceeded, and we call this the characteristic dead load. In terms of the live load, particularly with people loading, in the week of a building, you don't expect loads to be high. But in the year of a building, you may say, well, every year in this building, there's the big Christmas gala, and on that Christmas gala, we get hundreds of people in this building. So depending on what time period you're looking at in the life of a building, you may have heard most buildings have a 50-year design life. Okay? They're now slowly increasing that. I think one of the bridges in Brisbane has just been built for a 100-year design life. So the accepted practice is to choose a value of the live load that has a 5% chance of being exceeded once in 50 years. 50 years is chosen because that's the design life of most buildings, but fortunately a lot of old buildings in the city, you know, are older than that. Okay, so it's not to say that at 50 years the buildings suddenly need to be pulled down and don't work anymore. That's just the design life we build them for nowadays. Of course, years ago, they just built them. They didn't have so much statistical analysis involved. But anyway, we call this the characteristic live load. So whenever you're given a live load or a density of concrete, assume it's a characteristic dead load. So what does that characteristic thing mean? Well, it all is based on a standard or normal Bell distribution curve. And just as a bit of revision, we know a normal Bell distribution curve is symmetrical about the mean. And we know the standard deviation indicates the degree of spread. Okay? So in terms of what the standard deviation means here, you'll see 68 as a standard % of values occur within the mean plus or minus 1 standard deviation. So that means within this hashed region, you would have 68%, of the data points line. So you would get 16% being over-exceeded and 16% under-exceeded. Now we have to define the characteristic load as the 5% chance of exceedance. Thus, that means there's 90% lying within mean plus or minus 1.65 times the standard deviation and 5% above. So if you have to calculate a characteristic load when you have a set of data, and you'll be doing that in the practice class next week, you would calculate a mean, a standard deviation, and mean plus 1.65 times the standard deviation would give you the load you are going to apply to your structure. You can't apply an average load. An average load, as I said, would fail 50% of the time. So we have to put an extreme load on there, okay? And that extreme load is 5%. Now, you may be thinking, well, hang on a minute, that means 5% of the time our loads are still being exceeded. So 5% of the time the building might fall down. Is that a good risk? Characteristic loads that have a 5% chance of exceedance, that equates to 1 in 20 chance of exceedance. Would you be happy with that if you were building a building? No. No, so we're not happy with that. So what we do is we get our characteristic load and we then apply load factors to them. We always use the same characteristic loads regardless of what we're designing for, and we apply different load factors. And we call this limit state design. We design right up to the limit. If the yield stress, the maximum amount of stress it can carry is 300, we would do our calculations and ensure we can load it up to as close as 300 as we can. Where our factor of safety lies, it lies in the loading. Okay? So we call this limit state design. Our design loads are our load factors times our characteristic loads. So when our limit state is a set of performance criteria, strength, deflection, vibration, that must be met when the structure is subject to loads. We don't just design so the building doesn't fall down. You may walk across this floor and I go, assuming it's on the 10th floor of a building, and I'll go, it's perfectly safe, walk across it. And you start walking across it and it starts bouncing. And I go, don't worry about that, it's not going to fall down. Okay? You're not happy with that. So we design for deflection, for serviceability, as well as strength. And we put equal weighting on both designs, but the variation comes in our load factors. So limit state design requires a structure to satisfy two principal criteria, what we call ultimate limit state criteria and serviceability limit state criteria. Ultimate limit state criteria is a strength check. That's the failure design. To satisfy the ultimate limit state, the structure must not collapse when subjected to the peak design load for what it has been designed. And that peak design load is 1.2 times whatever the dead load is and 1.5 times whatever the live load is. So we now increase our load from dead plus live to, we increase our dead load by 20% and we increase our live load by 50%. And that is the loading we design to. Now, you may think that's very extreme, but the consequence of something failing is people being hurt, okay, is fatalities. So these load factors reduce the chance of the load being exceeded from 1 in 20 to over 1 in 10,000. So now our odds are a bit better, or a lot better. And that is the way we design in Australia. There used to be something called permissible stress design, but I won't go there. Okay, that's our ultimate limit state design. We also design for serviceability limit state design. That is to design so something doesn't deflect too much, so the structure is serviceable. So as well as in that, when you design a sports floor, you have to ensure it doesn't vibrate too much as well. So the limit state that ensures that users are comfortable with the performance deflection of the structure. So we use the same loading, we put different load factors on. So we assume we have the dead load, and now we actually take only 70% of the live load. And what we do is we then say, with that loading, how much does it deflect? Okay, it's less than what it has to be. So there's some upper limit, and we say it's less than what it has to be. So in actual fact here, this increases the chance of the load being exceeded from 1 in 20 to 1 in 5. So you may go, well, what are you doing here, Lizzie? You're putting less load on. But you have to remember that we're starting off with pretty extreme loading. So here, our live load is 3 to 5 kPa. Now, how often do you think in this region here you would ever get 5 people crammed into every square metre? Do you think that would actually ever happen in the life of this structure? You never know. So we have to assume that's the case, and for strength, we multiply that by 1.5. So when we're doing our ultimate limit state check, we multiply that by 1.5. So we reduce that up to, if we're talking with 5 kPa, we actually design it for 7.5 kPa, because you never know in terms of life. In terms of deflection, what do? We get our 5 kPa and we multiply it by 0.7. And that reduces it to 3.5 kPa. Which, do you think you'd ever get 3 people per square metre up here? You may. If that is exceeded, will the building fall down? What's going to happen? Well, if this wasn't a ground floor, what's going to happen is maybe the ceiling below me might crack a bit. Yeah? So it's not a catastrophic failure that we're talking about. So that's why we put smaller load factors when we're designing for deflection. Now, if you've got that many people crammed in here, do you think they'll notice that the floor's deflecting a little bit more than it would otherwise be deflecting? No, they're probably worried more about someone putting their hand on their bum than anything else. So can you see? That's why we put different load factors for these two situations. When it comes to strength, for failure, we increase our load dramatically. When it comes to deflection, we treat it as at a reasonable. We have a lower level of loading on there because the consequence of failure is not catastrophic. Something might crack, a pipe might burst. So, in summary, dead load, soft weight, permanent fixtures, live load is the removal part of the load. All unfactors loads, assume them to be characteristic loads. That's loads that have a 5% chance of being exceeded. So if you're given a group of numbers, you can work out the mean and the standard deviation to work out what your characteristic load is. And as I said, you'll be doing that next week in the practice class. We apply the load factors to the characteristic loads to increase safety, and we use limit state design. So primarily things are designed for ultimate and serviceability limit state. One is designed against collapse, one is designed against excessive deflection, one has the bigger load, one has the smaller load. Now at this point here, people say to me, but hang on a minute, Lizzie, this case is never going to be critical here because the loads are a lot smaller. What you will realise when you work through the procedure is when we say we have two different designs, we actually do two different checks on them. This one here, we check our stresses are less than the allowable stress. Over for serviceability limit state, we actually physically calculate how much something deflects, and we ensure it's less than a maximum deflection here. So they're two independent checks we do, two completely separate independent checks. And if something is within the range of both, our building is acceptable. If you say, no, the beam deflects too much, then you have to put a bigger beam in, bigger than is required for strength. Or no, it's going to fail, but it's not deflecting too much. You still have to put a bigger beam in, and it'll deflect even less. So these are two independent checks you do, and you'll be doing that with your third project. Okay, so we're going to do some worked examples now. We're going to actually do some calculations. Before we do, quite often you'll see beam designations. The standard steel beam is a universal beam. If you're parked in the car park, engineering car park, all the beams in there are UBs. So when you're given a UB designation, the first number represents the depth of the beam. So if you had a 310 UB40, that's telling you it's a universal beam. That's telling you it's 310 millimetres deep. And the 40 is telling you it weighs 40 kilograms per metre. So that building friend of yours that asked you to lift those precast panels has run you up again. I've got a couple of UBs I need to move. Ask him what the designation of them is. If it's a 510 UB100, it means it weighs 100 kilos per metre. Again, sorry, I'm busy. I can't help you that day. If they're small beams, okay, and they weigh 15 kilograms per metre, so if it's a 210 UB15, they're lighter weight. Okay, let's do a problem. This is taken off a very old exam paper, but this will give you some idea of the type of exam questions we have. Now, what I can do here, I'm just going to try some new room tech. I'm going to freeze. Right. Okay, and then I'm going to give myself... Oh no, that didn't work, did it? Hang on, let me try that again. Freeze. All right. Actually, I don't want to freeze the right because that's the side being recorded. I want to unfreeze it and I want to freeze the left. I'll get this right in the end. Choose to display freeze on the right. No, there's no option for left. We could freeze the right and all the people that have decided not to come to the lecture will just miss out. Oh, but I won't be that mean in the first week. Will I be that mean in the first week? Oh, you are mean. No, I can't. I better not, because you know what? Then people email me and complain. So we can't freeze it. I was looking forward to using that feature. Okay, let's go back to the question where you can read it bigger now. We have a concrete slab. It's 300 mil thick. If you look at the diagram, you have to start being able to understand and read information like this. It's 5 metres wide and it's 9 metres long. It's used to support a live load of 4 kPa, kilonewtons per metre squared. I'm going to be saying kPa because kilonewtons per metre squared is too much of a mouthful. The concrete slab is supported by 2 brick walls. Well, they're hardly walls, but 2 upstands, 200 mil by 500 mil by 9 metres long. If you look at the diagram here, you'll see it's 500 mil high and 200 mil wide. And that, in turn, is supported by a steel beam under here. Given the density of concrete, 24, the density of brickwork, 19, and the weight of the steel beam, so they've told us how much the beam weighs, calculate the dead load and the live load on each steel beam in kilonewtons per metre. Okay? And then it says calculate the ultimate limit state design load. So you're going to calculate a load up here, we'll call it W, kilonewton per metre. And when you calculate the ultimate, you're going to calculate a dead load component and a W live load component. And then when you come here to calculate your ultimate limit state, that will be 1.2 times your dead load component plus 1.5 times your live load component. And that will be your ultimate limit state load. And that's on the basis that you now have a beam 9 metres long and it now carries a load W alt. So that is then your starting point to check the stresses. Once you have your load on your beam, you go, okay, we can now start working out what the bending stresses are on this beam because it's bending. So you have to turn your load in your weight, your real life loading, into an idealised number. So we clear where we're at now? Okay, so let's get going. And just to repeat again, these inkings, I'm a bit messy. I just can't neaten up my writing. I'm sorry. I'll try and make it neater. I will usually put them online. There's a little folder in the lecture area. I'm not sure if it's hidden or you can see it yet, and it's empty, called Lizzie's Inkings, Lecture Inkings. And then what I'll do is I'll get these PowerPoints and I'll take everything else out except the slides that I've written on, and I'll put them in there. So by all means copy them down, okay? But be aware that they're there as well if you think you've copied down something incorrectly. And also these lectures are being recorded as well if you choose to hear the whole thing again. Okay, so we want to calculate the weight. First of all, what's the question? Calculate the dead load and live load on each steel beam. Now the first thing you have to be aware is, it says the weight on the steel beam. This actually includes the weight of the steel beam. So always include all the loading, all the self-weight loading. Before something can carry more load, it has to be able to carry its own self-weight. So our dead load here, often called G, will be equal to the weight of the steel plus the weight of the bricks plus the weight of the slab. And we're trying to calculate that in kilonewtons per metre. So looking at our steel weight first in kilonewtons per metre, we've been told it weighs, over here, 60 kilograms per metre. So we already know how much our beam weighs. We don't have to do anything to it apart from convert to kilonewtons per metre. So we get our 60 kilograms per metre. We multiply by 10 to convert to newtons, and then we divide by 1,000. So that will give us the weight here as 0.6 kilonewtons per metre, and that's for the steel. Oh, no. Oh, hang on, I haven't got it on pen, have I? Pen. Now, and now it's not red. The bricks now. I want another colour. Fussy. Give me a blue. Okay, our brickwork now. Our bricks work weighs, we were given the density as 19 kilonewton per metre cubed. So I'll do it the long way now. We need to know the volume. Now remember, we want to know the load, be clear, on each steel beam. So we're going to work out the weight of the bricks on one steel beam. So the volume of our brickwork is 0.5 times 0.2 times 9 metres long. And that now, when I multiply out, will give me a load in kilonewtons. And I want it in kilonewtons per metre, so I'm just going to divide by 9 there. And that will give me a load of 1.9 kilonewton per metre. Now can you see here that I've divided by 9 and multiplied by 9 here? So the other way to have looked at this was to say 19 times the cross-sectional area, and that would have just been 19 times that little cross-sectional area there, which is just your 0.2 times your 0.5. So it's one extra step. If you need to do it, I don't have a problem with it, okay? Okay, then finally, we have the slab weight. So we want to know the weight of the slab on one beam. So we want to know half. So if you were doing it the quick way now, you would, in terms of cross-sectional area, just look at the cross-sectional area of half of the slab. So here, and it keeps on changing the colour when I jump slides. So you could say, well, our density here is 24 kilonewtons per metre cubed multiplied by our cross-sectional area. And that's equal to 24 times our width here was 5 metres. So that's 2.5 metres. And our thickness was 300 mil times 300. And that will give me a load of 18 kilonewtons per metre. The other way to do this is to say 24 kilonewtons per metre cubed times the volume, and we'll say the total volume, divide by 2 beams, divide by 9 metres. So that would be an alternative way to do it. And doing it that way, you will get the same answer. So doing it this way, you would get 24 times the volume of our slab is 5 times 9 times 0.3. So that's our total volume. Then we would divide by 2 beams and then 9 metres, and that would also give us a load of 18 kilonewtons per metre. So if I could freeze, let's just freeze the right one for the time being. Oops. Okay, so you can see our loads there. So our total dead load now is equal to our 0.6 for our steel plus our 1.9, and I should put units in here. Total dead load in kilonewtons per metre on one beam. Always tell yourself, remind yourself what it is you're trying to calculate. That's the brickwork plus 18 kilonewtons per metre. That's the slab. And that gives you a dead load of 20.5 kilonewtons per metre. Does that make sense? Can you see where I pulled everything from? Okay, now I will unfreeze for the people that aren't here. Then we need the total live load in kilonewtons per metre on one beam. So our live load, you can't see this, but to remind you, was 4 kilonewtons per metre squared. And we want our live load on one beam. So the quick way, 4 kilonewtons per metre squared times the breadth or the width over which the live load acts. And what is that width, everyone? 2.5 metres. So it's simply 8 times 2.5, which is 10 kilonewtons per metre. Now again, alternatively, and I don't mind how you do it, and I can't reiterate that enough. I have 4 kilonewtons per metre squared. I'm going to multiply it by the entire area, 9 times 5. Now that's given me a load in kilonewtons on the whole thing. I have 2 beams, so I'm going to divide by 2 beams, but that's still a load in kilonewtons, so I then have to divide by the 9 metres. And that will give me the same answer, 10 kilonewtons per metre. So finally, our ultimate limit state loading in kilonewtons per metre on, rather than get the eraser, I'll just, on one beam. This is our final answer. Well, that's equal to 1.2 times our dead load of 20.5 plus 1.5 times our live load of 10, which is a value of 39.6 kilonewtons per metre. And that now is the starting point. That's this load here, WLT, for our 9 metre long beam. That's the starting point for the analysis. Any questions with that? Come after if you have any questions with that. Okay, bit of light relief. When I was in Newcastle seeing the Angel of the North, of course you have to go into Newcastle itself. It's a lovely town. And the Tyne River passes through Newcastle, and within a 1 kilometre stretch there are 5 bridges. So if you like your bridges, it's a good place to go and see your bridges. You can see them down here. You can see the Sydney Harbour Bridge here, and you can see a lower bridge in red here, and to let boats through, this lower bridge in red rotates on a vertical axis, opens up, and then you have this arch beam bridge up here that's a lot higher so the boats can get under. And this Gateshead Millennium Footbridge was completed in 2000 as part of the Millennium celebrations, and it's low, and they had to allow boat traffic through. So it is the world's only tilting bridge. So what it does is it tilts up on these pivot points down here. It operates like the lid of a giant eye, slowly opening and forming an arch under which the ships pass. So of course the architects had a great time designing that. Took it to the engineers, and the engineers said, yeah, we can make it work. So what did you hear? It is part arch, part suspension, and this deck in here, well, it's beams in between the suspension. Because there's a curve in it, there's also torsion and twisting forces occurring. So this would have been analysed using complex modelling on a computer, by a computer, not something that could be done by hand very easily. So the bridge itself, I think, is quite delightful, but interesting is how it was constructed. So on both sides of the river you can see a lot of structure, so there wasn't much room to build this thing. So what they did was they carried the completed structure upstream by using the world's second largest floating crane, which has a deck the size of a football pitch. So they shipped it up there, and then they would have had a crane here or on the actual barge, and then they would have lifted it into place. They would have built the fixing here, the pin connection here, soldered it in, stuck this pin in here in on both sides, and there's your bridge. I don't think it would have been that easy, but there's your bridge. So this bridge here rotates. It takes 4.5 minutes to rotate from 40 degrees from the closed to the open position. And it just uses some simple hydraulic rams in here, powered by a 55 kilowatt motor. So not a lot in there. So that's the Gateshead Millennium Footbridge, which I think is a lovely structure and more unusual because of the way it tilts open and closed. So if you're ever in Newcastle, go and have a look. And if you ever want to design something like that, you've got to know how to design a timber plank on a steel beam. So this is the second and will be the last example. So would you like a 5-minute break? Okay. Have yourself a 5-minute break. Okay, let's get going. So someone just wanted clarification just in this previous problem. There were 2 steel beams here, and each beam weighed 60 kilograms per metre. Okay, if we just go back to the bigger picture. So there were 2 beams here, and you were looking at the weight on one beam. Because you only need to design one beam because they're identical. So you'd work all the loading out on one beam. Okay. So, example 2. We have a timber plank, 200 mil thick here, 6 metres long, the timber plank itself, but it's been supported, it's supporting a live load here of 5. So the live load here is 5 kPa, kilonewtons per metre squared. The plank is then supported by 2 equally loaded steel beams, each 10 metres long. And they tell us the weight of the steel beam. So this steel beam here, each of them weigh 100 kilograms per metre. Calculate the dead load and the live load on each steel beam in kilonewtons per metre squared. So this time round, if I drew my steel beam, 10 metres long, I can't say, well, it's got one load over the entire steel beam. That would be wrong. Because as you can see, one side of the beam is more heavily loaded than the other side. So when you come to do this problem, you have to say to yourself, okay, I have one load that runs the entire length of the steel beam, and that is the weight of the steel itself, which is my 100 kilograms per metre. Then on that steel beam, over the 6 metres, this is then where I have the weight of the deck, and then the weight of the live load. So when we draw it up this time, we actually have to draw a picture of it to show where the load is acting. So we're asked to calculate the dead and the live load. So when I come and do the dead load, my dead load I will have a dead load 1 and a dead load 2 component, and the dead load 2 is just the steel weight. Then when I come and work out the live load, I just have a live load acting on the left-hand side 6 metres of the beam. Does that make sense? Okay, what people tend to do is they take the average of it and they spread it evenly. That's not what is there in reality. You have to model what is there in reality. Okay, let's do some numbers. Calculate the dead and live load, part A on each steel beam. So it's telling us again on one beam. And it says on each steel beam. Once again, that includes the weight of the steel beam in kilonewtons per metres. And then calculate the ultimate design load in kilonewton per metre on each steel beam. And they were kind to you that year. This is a very old exam question, and because it tells you what the appropriate load factors are. I'm not sure we always tell you what the appropriate load factors are. We expect you to memorise 1.2 plus 1.5. It's not that hard. Then draw a diagram showing how the design load is acting on the beam. So they're telling you to draw it. Is everyone clear what the problem is? Yeah? Okay. So I think next week when this screen is working here, we'll be able to freeze that big picture. I was looking forward to freezing it today. Simple pleasures in life. Okay, so we have our G, which is our dead load, and that comprises the steel and the timber. So, our steel weight, well, that is our 100 kilograms per metre, and we know we multiply by 10 to convert it to kilonewtons, and we divide by 1,000 to convert to newtons, and divide by 1,000, so we get our final answer in kilonewton per metre. Now, someone asked me about units earlier. They were doing a question in the book, working hard, which is what I like. There is a document on the Moodle site somewhere. I'm not sure where, if it's under resources or lecture material. It's called simply units.doc. Unit? I think it's called units.doc. It's, I think, a 3 or a 4 page document, and it just runs through unit conversion and things like that. So it might be worthwhile, if you're a bit rusty with your units, just downloading it and having a look at it and deciding if it's worthwhile printing it off. Okay? So we know the weight of our steel. Now, how about I give you a minute and you work out the weight of the deck in kilonewtons per metre on one steel beam equals, and what I'll do is I'll go back to the big slide so you can see the dimensions. So can you tell me what the load is in kilonewtons per metre, the weight of the deck? Sorry? Oh, you've worked it out already. 0.3? No? On one side? Someone over here said 4.5. 4.5? Okay, so what we do is, I'll do it both ways again. If I was dealing with just density times cross-sectional area, the cross-sectional area on one beam is this area in here. Yeah? And that area in there is 1.5 metres times the thickness of the deck is 0.2 metres thick. So that's my area, and I multiply that by the density of the timber, which we're told is 15, and that gives me a value of 4.5 kilonewtons per metre. So that's the quick way there. What I'll now do on the next overhead is I'll come in here and I'll do it the slightly longer way. I have the density. I'm going to multiply it by the total volume of the deck. 6 by 3 by 0.2. That's the volume. So by doing that, I now have a load in kilonewtons. So I want it on one beam only, and that's the load on 2 beams. So I'm going to divide by this. I'm writing beams in there so you can see it's 2, not 2 metres. So I divided by 2 beams because I'm after the load on one steel beam. And then I wanted per metre length. Now this is where people tend to then go, well, the length is 10 metres. No, it's the length over which the load acts. So that's our 6 metres. So when you do that, you get your 4.5, kilonewton per metre. So if I now draw the dead load here, I will draw a dead load on this side equal to 4.5 plus 1, which is 5.5 kilonewtons per metre. This is the dead load. And then on this side, where we only have the steel beam, that weight is 1 kilonewton per metre. So there's our dead load diagram. Let me just check if I have another. Okay, I can spread out. Now our live load, Q. So the live load we had acting was, remind myself, 5 kilonewtons per metre squared. So I'll do it the long way. We want to know what the live load is in kilonewtons per metre on one beam. So that's equal to our 5 kilonewtons per metre squared. The total area over which that loading acts is our 3 by by 6 metres. Now that gives me the total load on the whole system. So I'm going to divide by 2 beams. That unit now currently is still in kilonewtons. I want it in kilonewtons per metre, and the length over which it acts is 6 metres. So that gives me a live load of 7.5 kilonewtons per metre. Now, alternatively, what did we say? The live load in kilonewton per metre is just our 5. It's just our 5 kPa multiplied the width over which it acts. So what is the width over which it acts on one beam? 1.5 metres times 1.5 metres, which gives us 7.5 kilonewtons per metre. Do it whichever way you want. And that live load diagram now, that force is acting only on the 6 metre part of the beam. So the rest of the beam just only has steelwork there, so there's no live load acting. So just now, finally, part B was asking us for the ultimate limit state load, which is our 1.2 dead load plus 1.5 live load. So people see those numbers and they just want to stick everything in those numbers. You can't deal with this without the diagram now. So on this diagram, I have 5.5 kilonewton per metre dead load on that side. I have 1 kilonewton per metre dead load on that side. And I should put my dimensions in there, 6 metres and 4 metres. And then on this side, I have my live load here of 7.5 kilonewtons per metre live load. So that's my final ultimate limit state loading. Here it's just 1.2 times 1, because all I have is dead load, kilonewton per metre. And over on this side here, it would be 1.2 times our total live load of 5.5 plus 1.5 times our, dead load of 5.5 plus 1.5 times our live load of 7.5, which is a load of 17.85 kilonewtons per metre. Now, just to clarify, when you go and do your strength calculations, you don't know how to do them yet. That's what I'll be teaching you. That's your starting point. So this here is your starting point for your ultimate, and I should unfreeze that now, shouldn't I? So this here is your starting point for your, I like changing colours, for your ultimate limit state design. But just be clear, you're designing that beam to carry that loading and it won't fall down with that loading, okay? But I go and stand on that deck and this thing is saggy baggy, okay? And I'm going to have this is going to be floating in the middle of a river and I'm going to have the band playing on this part of the beam and, you know, they're going to be very uncomfortable with it sagging everywhere. So it's important it doesn't move around too much. Move around, it's important it doesn't sag too much, or my band is going to want to go on it. So as well as doing a strength check, I have to limit how much that beam deflects. And the criteria is normally span on 200. So that beam is spanning 10 metres. So that is a span in millimetres of 10,000 millimetres. And I divide that by 200, 1, 2, 1, 2. So this thing cannot deflect more than 50 mil. If it deflects more than 50 mil, it's considered uncomfortable. It's considered unserviceable. So when I do that deflection calculation, I'm not going to put this big heavy load on there. The load I'm going to put on there is dead load plus 0.7 live load. So the dead load over here, the loading on the left-hand side, would just be my 1 kilonewtons per metre, and the load on my right-hand side would be 1 times 5.5 plus 0.7 times my 7.5, and I don't have a number here for that. Okay? But when you come and do your deflection calculations, you would base them on the lighter load. When you come and do your strength calculations, you would base it on the heavier load. Now say from that dead load calculation, the beam there isn't strong enough. When I do the deflection, it only deflects 40 mil. So in terms of deflection, it doesn't deflect too much, but in terms of strength, it's not strong enough. I have to put a bigger beam in. This time round, I do the strength calculation. The beam is well and truly strong enough. However, when I do my deflection check, it deflects 60 mil, 70 mil. So it's deflecting too much, I have to put a bigger beam in. So when you come and do the design process, you don't go, oh, it's only deflection, it doesn't matter, don't worry about it. You have to meet serviceability limit state requirements and ultimate limit state requirements. That's strength requirements and deflection requirements. You don't say, oh, who cares about deflection, it doesn't matter. It matters just as much as strength. But we've put smaller load factors on there. So when we do that deflection check, we're not actually doing it for as much load. Okay. I'm not going to do that one. That's the end. Next lecture, you will then get those loads. Shh, hang on, let me say one more thing. And we will learn how to calculate the reactions. That's the next step in our design process. We'll learn how to calculate reactions.